Hi, the lecture today is about calculating volume by the method of cylindrical shells. Well, when we are facing the issue of finding volume of an object, we have many methods available to us, and they are each suitable for a set of circumstances. We have already seen one method, the one that we saw in the previous lecture was the method of calculating volumes by using discs or washers. There the idea was to cut up the solid of revolution by slices. Each slice is going to look like it would look like a disc, or in case that the object was hollow, inside the disc could have been empty. And then we'll calculate the volume of each of these disks and add them all up. Today we are going to look at another style of doing these things, which is by method of cylindrical shells. What's a cylindrical shell? Well, take a cylinder, ordinary cylinder or can, and imagine that the walls of this cylinder are thick. So you're looking at an object more or less looking like this. So we are going to cut up our solid of revolution into a bunch of cylindrical shells like this, find the volume of each of them, and then add them all up to get the volume of the object itself. So what we need first is a formula for the volume of the shell itself. So what we need is a formula for volume of cylindrical shell. So that's going to be our first order of agenda, and then we are going to go after examples. Let's consider this shape again. Suppose that outside radius of this, going all the way to the outer radius, is say R2, and consider the inner radius of this thing to be R1. So what I'm going to try to do now is to find the volume of the shell. To do that, I find the volume of the big cylinder. You remember the volume of a cylinder was pi radius squared. So for the outside, the radius will be R2 squared times the height, whatever the height is. So we multiply this by the height, and then I go ahead and remove the volume of the interior cylinder. Presumably this has been removed. So that's going to be pi R1 squared times h. Now let's go ahead and manipulate this thing a little bit so that it will be useful in our calculations later on. I am going to go ahead and take a factor of pi and h, and now I'm left with R2 minus R1 squared. You know, this can be factored further, so I go ahead and do that. Pi h, this can be written as R2 plus R1 times R2 minus R1. Well, what is R2 minus R1? R2 minus R1 is just the thickness of this cylinder. So this is thickness. We are going to use a bunch of cylinders like this in our calculation, and each of them is going to be a thin cylinder. So the thickness of this is what in our calculations to be referred to as perhaps delta R, indicating the size of the wall of this cylinder. That's delta R. R2 plus R1, well, that's the sum of these two radius. To make something more visually understandable out of this thing, what I am going to do is to divide this by 2 and then also multiply it by 2 so that I'm not changing the expression. R2 plus R1 over 2 is going to be the average radius, that is starting from this point and going halfway in between. So that's the average radius. I might show this by, say, R. So the average radius is starting from the origin here and going halfway between the two walls of the cylinder. So let's go ahead rewrite all of this thing. I'm going to write 2 pi r next to each other. 2 pi r times h times delta r. Let's understand the meaning of each of these things. Well, this one, we say, well, that is the thickness. That's just the height of the cylinder. 2 pi r is going to be the size of the circle that is halfway between these two circles. So that is really a circumference of this middle circle. So I'm just going to refer to it as the circumference. It's actually, in the long run, it's not going to matter all that much if circumference of outer or inner or the middle. Let's just refer to this thing as their circumference. So remember that we are going to base all of our calculations on this formula. So I'm going to capture this. Now let's see, how are we going to make use of this formula. Before I start my problem, I'll remind you one more time. If you have a cylinder with a height h, radius approximately r, and a thickness which is delta r, then the volume of it is 2 pi r times h times delta r. So delta r was the thickness of this wall. So long as you remember that formula, you'll be okay in the future calculation. Let's take an example. Find volume of solid of revolution obtained by rotating y is equal to x squared, x between, say, 0 and 2, about y-axis. So this method of cylindrical shells, just as method of disks, are only good for solids of revolution. If the shape doesn't have that kind of symmetry, we can't use this idea. Consider this parabola. It's the parabola of y is equal to x squared, or x going from 0 to 2. We are taking this parabola and rotating it about the y-axis, so we are going to have a shape kind of looking like this. The volume we are after is what is generated by turning this region. Okay, we said we are turning y equal to x squared, where x is between 0 and 2 about the y-axis. We are taking this purple region and turning it around the y-axis, and we want to know what is the volume that is generated in this fashion. Well, what is the cylindrical shell gonna do for us here? The idea is that we take this thing and cut it up just as the way we were doing at the beginning of calculating areas. I'm gonna create lots of cuts like this, and while this cut starts to rotate, each one of them is going to make a cylindrical shell. Remember that the area, the volume itself has this axis of rotation. The axis of rotation is the y-axis, and then we can stack lots of cylinders just like this cylinder to fill up the volume we are trying to measure. For example, here's another one of these cylinders. You can take a rectangle here. During the rotation, this rectangle is going to create a shell. Okay, by now hopefully we understand what is involved in this particular type of slicing. What I need to do is to go ahead and find the volume of each of these shells by using this formula. I need to find that volume and then add them up together by using the idea of integration, and then I'll be all done. So let's go ahead and get all the ingredients. Suppose I concentrate on this shell that is here. Imagine the point at which this shell is drawn is at the point X. Now let's go ahead and find all the ingredients of this volume formula. What are the ingredients? 2 pi, that's a fixed number, 2 pi times r, that's the radius of the cylinder. What is the radius here? the radius is the distance of this point from the center of rotation. In this case, simply the radius is just r. Excuse me, the radius is just x. What is the height? Height of this cylinder, well, that is given by the function formula here, y is equal to x squared. This height is x squared. What is the thickness? Thickness, which we are showing by delta r in our original formula. The thickness of these things, remember we are placing these things on the x-axis. This is our x-axis. The thickness here is just dx. So the volume is going to be 2 pi. Instead of r I have x. Instead of h I have x squared. Instead of delta r I have dx. Now this is going to be element of volume for us. We have to calculate also the volumes like this and add them up to each other. It's much better if you go and call this thing volume of one of these slices or one of these shells, and for that reason we are using the notation dV, element of a volume, is equal to that. So dV is 2 pi x cubed dx. If you wish to think about dV, you can think about it as a differential of the volume. Now we go ahead and actually find the volume itself. Let's go ahead and do that on the next page. By now we learned that dV is 2 pi x cubed dx. So what is the volume itself? This is the total volume that is obtained by integrating this formula. What I'll have is going to be the integral. Remember, I draw the shape here again so that we have quick access to it. The volume was obtained by taking the region from 0 to 2 underneath y equal to x squared and rotating it around the y-axis. So the domain of integration is from 0 to 2. Let me show it to you again on the previous slide we had. We have these cylinders stacked from the innermost cylinder here. Some hard to draw, but there is a tiny cylinder right here with the radius close to 0, all the way to the biggest cylinder. The biggest cylinder is going to be of radius 2. So the radius of cylinder ranges from 0 to 2, and that determines the lower and upper limits of integration for us. So if I go from 0 to 2, 2 pi x cubed dx. I can put the 2 pi outside. Antiderivative of x cubed becomes x to the power of 4 over 4, and I have to put 0 and 2 in it. So that gives us 2 pi. I put 4, excuse me, I put 2 in this, I get 16 over 4. Then I put 0 in it, I get 0 over 4. And the whole thing boils down to, this is 0, this is 8, excuse me, 4 times 2, that's 8 pi. Okay, so that was for our first example. Now let's go ahead and do a quick reminder of what the method of washers or disc was all about, and why is it that we need another method. Let me go to another page here. suppose I ask you use method of disks or washers for finding the same volume. So let's remind ourselves what volume is it we are talking about again. This was y equal to x squared, limited from 0 to 2, and we are rotating this around the y-axis and finding this volume. In the method of washers, we are creating the disks by slicing the shape perpendicular to its axis. So here imagine I am taking a plane and slicing this thing at that plane. What am I going to see? I'm going to see a washer, kind of like this. Let me color the inside of this washers. That's the shape we are going to see. The idea there was to calculate the volume of each of these washers and then add them all up and find the volume in that style. What was the formula for that one? The formula for that for the element of the volume was pi times outer radius, outer radius referred to going from here all the way to the outer radius. This is the outer radius. Inner radius referred to starting at the axis and going as far as the inside circle. So that was inner radius. So I write outer radius minus inner radius squared. So that's going to give us the volume, the area of this shaded region. If I just multiply that by the thickness of, so these washers have some thickness, the size of this thickness would be just a differential of the axis of rotation. So here was your axis of rotation was y. The thickness of this disk is going to be shown as dy. So I'll multiply this thing by dy. Now let's go ahead and find out the ingredients here. Outer radius in this shape is just 2. In this shape we are going as far as 2 in all of our washers. So it's going to be 2 squared. It becomes a stickier issue to figure out the inner radius. From here to, let me draw it perhaps here. The inner radius will be the distance from the axis of rotation to the shape itself, to inner side of the shape. What is this? Well, from here to here you recognize it as x. Now we need to write this thing in terms of our variable of integration. What is x equal to? The shape itself is given to us as y is equal to x squared. So that tells us that x is equal to plus or minus square root of y. We are looking at the right hand side, so x becomes square root of y. Now if I take the inner radius and square it, that is square of x is just y itself, so I'll have just y times dy. Only one thing left to do, and that's to find the volume itself. Volume will be the sum of all such contributions. Each of them is pi times 2 squared, which is 4 minus y dy. Now what's the range of values of y? For this region, y starts at 0, and what's the highest value y goes to? Since x goes as far as 2, y is going to go as far as 4. So my integration goes from 0 to 4. Now let's go ahead and integrate this thing. Pi is a fixed number. 2 squared is 4. Integral of that is 4y. Y, antiderivative of that is y squared over 2. And I have to plug in numbers from 0 to 4 in this and subtract. When I put 4 in this, 4 times 4 makes 16. 4 squared over 2 is 8. And when I put 0 in it, 0 just gives me 0. The net result of all this is 8 pi. That is exactly the same as what we obtained in the previous round of calculation. Let me show you. We obtained that the volume was equal to 8 pi. That was obtained by the method of cylindrical shells. Now we did the same thing by the method of disks, and we got the same answer, 8 pi. At this point you might be thinking, well, if both of them are doing the same thing, why is it that we need two different methods and two separate sets of formulas to memorize and work with? And the answer is that in some cases one of these methods is a lot easier to apply, or perhaps the only one that we can actually apply to find the volume, while the other one is substantially harder to integrate. The ideas are very simple in both of them. It's just that some problems are more amenable to one as opposed to the other one. Let me give you an example. Suppose you were asked find volume of solid of rotation obtained by rotating the region between y is equal to x minus x cubed and positive side of x axis about the y axis. Let me quickly draw a picture for this problem. Here's our xy coordinates system. Now this formula represents the boundary of our region, y equal to x minus x cubed. If you spend a few moments to graph it, you see that it looks something like this. Now the region we are interested in is between this and the positive side of the x-axis. So the region we are really interested in is this region. So let me draw another picture. You have a region looking more or less like this. We are taking this and turning it about the y-axis. So when we're turning it, we are going to create a region more or less like this. We are asked to find the volume. We have so far two methods for finding volume. One is the method of disks, another one is the method of cylindrical shells. Which one of them is easier to apply here, or is it that both of them are equally easy or perhaps equally hard? Well, if you want to go by method of disks, you need to do the following. If you want to cut this thing by disk against the y-axis, you need to be able to figure out the inner radius and outer radius of each of these disks. Let me draw one of these disks. We need to figure out where is this point and where is that point. That is, if a line is drawn here, I need to know how close is this to axis of rotation, what's the x of this, and how far is this one from the axis of rotation, what is the x of that one. Which means for a given y, I need to find the x that satisfies this equation. Well, that's going to be a cubic equation to solve, and that's the difficulty. Let me remind you why the previous case was the easy thing to do. Let's in this case, if you draw a line here at y, if y is equal to x squared, it was easy for us to go ahead and find out what is x in terms of y, and that would give us either beginning or end of the disk. But in this example, if I start at this point and draw a line and want to find out the intersection with the shape itself, I need to solve a cubic equation, and that's going to be very hard and impractical for us to do. So what do we do instead? Instead of creating disks, we choose to create a bunch of shells. Let's go ahead and do it for these shells. So once again, we draw the picture bigger. We had y is equal to x, minus x cubed. Okay, we are going to limit ourselves to pictures in maybe just 2 dimension. So suppose one of the shells is having its wall at this point. This is x, this is going to be the radius, this is going to be the height, so element of volume is going to be 2 pi, radius is x, height is x minus x cubed, and then the thickness of the shell is dx. The integration has to be done from the beginning to the end of the region itself. This is the beginning, which is just 0. The question is, where are we ending this region? To find that one, I need to find the x-intercept of this. I take x minus x cubed, set it equal to 0. That is going to be our x-intercept. Factor x. Either x is going to be 0, which is just this point, or 1 minus x squared is going to be 0, which tells us x is either plus or minus 1. We are looking at the positive side, so x is just 1. So this point is just 1. So the limits of integral are going to be from 0 to 1. Now let's continue with the, I need to make a correction here. That's going to be the total volume. So the volume itself is going to be integral of 2 pi. This is x squared minus x, x to the power of 4 dx. That is 2 pi x cubed over 3 minus x to the power of 5 over 5 between 0 and 1. That is 2 pi 1/3 minus 1/5 is 2 pi 5 minus 3 over 15. That boils down to 4 pi over 15. So for this problem, the only method we could actually apply was the method of cylindrical shells.